last class, at the end of the class, we start talking about the multiplexer. The way we draw them in our book, and our book draws a multiplexer like this. In real life, it's a chip. But they make these lines instead of straight, they make them crooked to know that's a multiplexer. It has always one output. It has, we'll call this N select signals or control signals, select/control. And it has 2 to the N inputs. And they also have chip enable. If you don't turn on, nothing is going to happen. So a 2x1 mux will look like this. It has 2 inputs, 0, 1, and it has 1 select signal. And the way it works, when S equals 0, your output here will be equal to whatever pin 0, whatever you attach to pin 0. When S equals 1, your output will be whatever you attach to pin number 1. This is a 2x1 mux. Well, what does the inside of that looks like? Why is the output is always what you attach to pin 0 and 1? Let me call them, instead of pin 0, A and B, I guess. I don't know. What you have is an AND gate, attached to it A. This is a NOT gate. This is a select signal. That's what the inside looks like. We said when S is 0, the output is going to be whatever you attach to pin A, or pin 0. Let's call pin 0 here A. And this is B. Pin 1 is B. It's a better way of saying it. Now let's see if that's true. So when this is 0, your output, whatever you attach to A. When it's 1, your output, whatever you attach to 1, or B. Let's trace it. Let's see if it does work. I'll use red for this. When S is 0, this will be a 0 here, this will be a 1. 0 ANDed with anything, ANDed. 0 ANDed with anything is what? 0. 1 ANDed with A is what? A. When you add A or 0, what's the result?
Either 0 or 0.
A. Or. So it depends on the value of A. If A is 0, the result is 0. If A is 1, the result is 1. So you can see when S is 0, your output is A. Let's try, I use the black when S is 1. When S is 1, I got a 1 here. I got a B here. What is 1 and B?
1 or B.
B. When S is 1, what's the complement? 0. What is 0 and A? 0. An OR gate with 0 and B going to it. The result is B. So when S is 1, your output is B. When S is 0, your output is A. Do they come bigger sizes? Absolutely. We got a 4x1, 8x1, 16x1.
Now, is A and B always 0 and 1?
Nope. Yep, 0 and 1. Can't be. That's a binary digit.
It can't be 1, 1.
Nope. Now a 4x1 multiplexer Since you have 4 inputs, that's 0, 1, 2, 3, 4 input, you will need how many control signals here? 2 of them. Let's call them S0, S1. And let me label this W, X, Y, Z. You have 1 output. So here's what the truth table for that, what will look like. I'll make a table because it will be easier. So when S0, S1, and your output, when they're both 0, that says your output should be what?
0.
Whatever attached to pin 0, which is what? I'm going to call that W. 0, 0 says your output should be whatever you attach to that pin. If you attach it to ground, it's ground. If you attach it to 1, it's 1. When it's 0, 1, your output is going to be whatever attached to pin X. One zero, 1 1, 1 0, your output is going to be whatever attached to pin Y, and 1 1, your output is going to be whatever attached to pin Z. What does the inside of that looks like? What's the inside? You're actually going to have S1, S0. I know what to do. I got it. I'm thinking in my head I should have left more space for it. There's going to be 4 AND gates. They all what? Or together? So what are you going to attach to this? It's going to be this one, and the third one is what? W in this case. W will be attached to that. Notice when S1 and S0 both zeros, the complement is attached to that. That's 1, 1, that depends on what W is. So whatever W is, that's what you're going to see. This one, this, and what's attached to it? X. Backward. I have S0 as the first one. When this is 0, 1, right? I want 0, 1. Now 0, that's a 1, and this is 1. You end up with a 1 and a 1 here. 1, 1 and X, that'll give me an X. This one you want it to be on when it's what? 1 and 0? That's when you attach this to 1, this one to 0, and this, the last one, will be attached to what? Y. So 1 and 0, I want this one to be on. That'll be a 1, and a Y, and that'll give me a Y. And the last one is 1 and 1. One, and Z, and that'll give me a Z. So that's the inside of that mux. Four by one is 4 AND gates, 1 OR gate. This one fits inside that. How are we going to use it? Well, let's see. Let's take this problem we just did. And if I want to build this in the lab, I will need 2 8 by 1 muxes. 8 by 1. Because it goes 3, 5, 7, 6, 7, you know. So here we go. That problem, the sum of what? A, B, and C. What was it in that example? It is the summation 1, 2, 4, 7. And the carry out of A, B, and C is what? 3, 5, 6, and 7. This is an 8 by 1, that's an 8 by 1. I need 1 for each one of these. You can only have one output, so if you have more than one output, that's why you need 2 of them. A mux has only one output. You can't use it for both of these. So let's say this is the sum. I get 3 control signals, or select signals, A, B, and C. I got 8 inputs, 0, 1, 2, 3, 4, 5, 6, 7. We said S depends where you attach these pins. Now you want the sum to be 1 when what? When it's 1. So how about we attach to this to VCC? That's a 1 volt. We attach pin 2 to VCC. We attach pin 4 to VCC. And we attach pin 7 to VCC.
I thought there was supposed to be 2 muxes.
Yep, I'm just working with the first one. So what's the result? Or the rest of them? The rest should be attached to where?
Ground.
To ground. Did I leave anything out? So when A, B, and C are 0, 0, 0, your output is going to be whatever you attach to pin 0, which is 0, ground. When it's 0, 0, 1, that's a 1. Your output is going to be whatever attached to pin 1, which is 1. When it's 0, 1, 0, that's pin number 2. Pin number 2 attached to 1. Your output is 1. When it's 0, 1, 1, that's 3. This will be whatever attached to pin 3, which is ground. 4, that's 1. 5, that's ground. 6, that's ground. 7, that's 1. That's for S. And I need 1 now for C out. Remember that 7-segment LED we did last week? This would be a perfect 1 for it. 1 for each one of them. I need 7 of them. I don't have to simplify anything. So this is going to be VCC where? A 3. Five, 6, 7. The rest should be what? Ground. And now we got the sum and the carry out using 8 by 1 muxes. This is an 8 by 1 mux. 2 of them.
So their difference is that they have one alpha, correct?
Yep.
That's the only difference. they
So
have.
you can only, if you have 4 functions, you need 1 for each one of them. Where when we did this with a decoder, notice that you can have as many outputs you want to. Just put OR gates. Where was that? When I did that function with a decoder, you only need 1 decoder. And if I have 10 functions, I can have 10 OR gates and attach the right pin to it. So one of these, lots of these. With the multiplexer, is different. Each function, each output should have its own multiplexer. Now here's my problem. We go to build this in the lab. We walk in. I do not have an 8 by 1 mux. I have a 4 by 1 mux. Can I still build this using a 4 by 1 mux?
Probably.
I still need 2 of them, 1 for each one. So let's look and see if it can be done. Let me look at the function closely here. Maybe I can see something. The sum is equal to 1, 2, 4, and 7. I have color options here. I can take few 2 by 4 and make 3 by 8 out of them. Or I might say, let me be creative and use 1 2 by 4. I mean 4 by 1. We're not doing decoders, we're doing multiplexers. Use 1 4 by 1 mux for each one of these. I don't want to make 2 by 8. 8 by 1. 2 by 8. So I'm going to use 4 by 1 for each one of these. Only. So I don't want you to take a lot of 4 by 1s, try to make an 8 by 1 mux out of them. So how can I do a 4 by 1? Only 1 4 by 1 mux for each one of them. Only 1.
Do only those outputs, like 1.
I should write only 1 so you'll know. 1. Only 1 4 by 1 mux.
Do like 1 2 4 7 for each month. Well, for that first month, without having all of them.
Well, let's look at it closely and see if that's what we need to do. Let's put the truth table there. 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0, and the last one is 1 1 1. Let's look at the sum and the carry out. Zero, 1, 1, 2, 3, 1, 5, 6, that's 1, 7. 0, 1, 2, 3, 4, 5, 6, 7.
Now, how come those are ones again? Because they have multiple ones. Is that why?
What do you mean?
Oh, never mind. I see.
Now, let me look at the sum one. I'm going to use a 4 by 1 for the sum for now. So I have 2 control signals, because it's 4 by 1. I have 4 inputs. And I can use my control signal anything I want to use. I can use A and B, I can use A and C, I can use B and C. I'm going to choose A and B. And my reasoning for that, it is easier on my eyes if I use A and B. Why? When A is 0 and B is 0, we're talking about what? These two. See them? A is 0, B is 0. If I use B and C, then I have to look where? I have to look at this and add this. That's when they're both zeros. Everyone see why I chose A and B? Because they'll be next to each other. If I use B and C here instead of A and B, I go, okay, let's find out when B and C are 0. Well, B and C are 0. That's this case, number 1, and down here, which is number 4. What is it? Move C to the ground? That won't do it. So what I need to do is look right here. Look at S. Well, let's look at S compared to C. What do you notice about S and C here in the first two? When C is 0, what did you got?
0.
S0. When C is 1, what did you got?
1.
S1. That means I need to attach the first pin to C. Let's look at the second group, the 0, 1. The 0, 1,
When A is 0.
when C is 0, what you have? S is what? 1. When C is 1, S is what?
0.
0. How is that in relation to this?
C naught.
Yep, C naught. Now let's look at the next group. That's these two. I make them color
Same
code.
thing.
You can see the
It's
color
C
code.
naught again.
1, 0, 0, 1. Yep, that's C naught. And the last one is what?
C.
C. Let's look at the carryout. What about when they're both 0? Look at C out. Compare it to C. Doesn't matter what you do. The result is what? 0. Right? C out for the first two cases 0. So when this is 0 and 0, C out is going to be 0. Doesn't matter what you put for C. The next group. Let's look at C out in relation to C. What is that?
Same.
Same thing. Attach C here. The next one. That's what?
Same.
C. And what's the last one?
Always 1.
VCC.
How do you know if it's VCC
It's
or
1.
ground?
And this actually a 4x1 mux. 4x1 mux. I don't need two. One mux did it for each one. Again, I could have used my control signal to be A and C. If I chose A and C, that means for when both 0, 0, I gotta look at this one and look at this, try to compare them. I go, oh, that C out is 0 here. 0, 1, 0, 1. Where's 0, 1? I got to compare this now to B. Compare it to B. It says, don't really care. When B is 1, I got a 0. When B is 1, when B is 1, I got a 0. When B is 1, I got a 1. So it doesn't matter. So it's easier, instead of bouncing back and forth, is to pick two adjacent to each other. Now, could I actually when they're made an 8x1 mux out of 4x1? Or could I take two 2x1 mux, make a 4x1 mux out of it if I don't have them in the lab? Let's do that. I want to create a 4x1 using only 2x1. Here we go. I don't want to go crazy with it. Create a what? 4x1 mux using 2x1 muxes. So basically, this is what you have. You want this one. I'm going to make the picture. I'm going to show you what the inside looks like. You have four inputs, W, X, Y, and Z, and you have one output. And you have two control signals. That's what you want. Signal 0, signal 1. But we don't have that. Could I actually design this, build this, using only, I should write the word only, only 2x1 muxes, no gates, nothing even. Well, a 2x1 mux looks like this. These are the input to it. There's one output. Another 2x1 mux. Now, each one of these has one control signal. So what are you going to attach that control signal? S0. Let me put them right there. I'll do like this. That's my S0. Go into each one of them. Now, what about if I take another 2x1 mux and use S1 as my control signal? Would that do it? And let's trace it. Just refresh in case you forgot. S0, S1, and your output. When it's 0, 0, it's supposed to be W, right? 0, 1 is supposed to be this pin, which is X. 1, 0 is supposed to be this, which is the third one, that's Y. And 1, 1 is supposed to be the last one, which is what? Z. That's what the output should be. Do we have that with this design? Let's look at the first one, 0, 0. If you put a 0 here, I'll erase it. That says my output for this one is going to be whatever attached to pin 0, which is W. And my output for this, whatever attached to pin 0, which is what? Y. Now, S1 is what? I'm putting 0, 0 here, right? I'm going through the first case. S1 is 0. My output for this is whatever attached to pin 0, which is what? W. Is that what you're supposed to have? Yep.
Wait,
Let-
how is it? Sorry, I'm just. How is it?
Let's
0,
let's try 0, 1. There we go. 0, 1. So this is 0 and this is 1. When this is 0, actually I'm backward. This is 1, 0, right? S1 is the most significant. So 1, 0. 1, 0. When this is 1, that's 1 going to both of these. It says the output of this is going to be whatever attached to pin 1. This is pin 0, pin 1. 0, 1. When this is 1, your output's whatever attached to pin 1, which is X. When this is 1, your output's whatever attached to pin number 1, which is what? Z. Now they come to this one. This is 0. Your output for this is going to be whatever attached to pin 0, which is what? X now. Is it supposed to be X when it's 0, 1? X. Oh, I already have. Let's try 1, 0. S0 is 0. And this is 1. So this is 1 now. And that's 0. I don't know why I erased these. It says the output of this, whatever attached to pin 0, and that's W. The output of this, whatever attached to pin 0, and that's what? Y. Now this is 1. Your output is whatever attached to pin 1, which is what? Y. Is it supposed to be 1, 0, Y? Yep. And the last one, if it's 1, 1. 1, 1, and 1. When it's 1, this should be X. When it's 1, this should be Z. When this is 1, it says your output is whatever attached to pin number 1, which is Z. So 1, 1 should give me a Z. And that's exactly what we have. So we design a 4x1 using only 2x1. We can actually go through that, be creative, and design an 8x1 using 4x2, you know? Or we can take a stack of 2x1s, keep merging them down to make an 8x1. If I take 4 of these, back to 2, back to 1, I can do actually an 8x1 using only 2x1. I do these on the test a lot. I said design a 4x1, 8x1 mux using only 2x1. You're definitely going to see that on the test. I don't know if it's mux, decode, or whatever. I do that all the time. Or I want to do this, and that's what I have. I won't make it easy. If I have 8x1, I won't say, I got an 8x1, build this one, like that decoder we did early. Or the mux. This might be a 3-part question. Using 8x1. Second part, use 4x1. Third part, use a 2x1 and some gates. I can build this one using a 2x1 with some gates.